Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this session. Earlier we in the basic PLL we have looked at different blocks for PD and PFD. So, let me just look at basic PLL block diagram. I will first draw that. Okay. So, you have PD or PFD. Now, since we know that PFD is more beneficial when we want to detect the frequency and the phase error detector using the same block. So, I will go with PFD now. So, we have the PFD. PFD output actually gives us two signals up and down, and these up and down signals they have to be somehow interfaced with the loop filter, because your up and down signal, average of up and down signals, that has the information about the phase error. This goes to VCO and then you feed it back. So, this is your reference, this is your output, right. So, the question which we have now before us is how we are going to convert these up and down signals to some voltage signals and then get it filtered by the loop. So, let us look at it what these up and down signals are and how they look like. So, for example, we have seen this, but I will just redraw it. So, you have this R signal and you have out signal. At any given time, if you have a phase error, then your waveform may look like this. Okay. In response to this R and out signal, I am going to have up signal like this, okay, and okay, this is periodic. So, I am going to have up signal like this, and then the down signal will happen to be something like this, very narrow, but both of them come down at the same time, right. So, this is what I will have. Practically this will happen. Now, up and down signals, if you look at it, these up and down signals have the information about the phase error in the pulse width. I want to convert this phase error to a voltage, okay. That is what I need to do, because loop filter is going to process the voltage. So, I have a couple of options before me. If you think, if you look at it, one option before me is, so up and down, since they are digital signals, they have high and low, they can very well control the switches. So, I come back to my switches. So, I have a switch which is controlled by up and I have another switch which is controlled by down. Depending on when my signal is high, high means you like this and low is this value. So, do not consider anything else, high is this value and low is this value, okay. So, should be clear. So, now these up and down switches, they connect a voltage source, for example, Vp. Let me just draw the circuit first. This is grounded, this is Vp, both are Vp, and then you have some filter here, R1, R2 and C, and this happens to be your loop control voltage. So, I converted from voltage up and down signals to even the loop filter output. So, let me just write this as V control, VCTR. Okay. So, if you look at it, what is going to happen during this case? This is one option in which we can convert the voltage up and down waveforms to voltages. So, here I will just amplify the time during which up is high. So, this is the duration for up, right, and then you have down signal. During the down signal, you, let us say this happens. I will neglect this particular part, but this is just the amplified part. During this time, both the switches are high. So, when up signal is high, what happens is the switch which is controlled by up signal gets closed. When the switch gets closed, your circuit becomes like this. Switch is closed, you have this as ground, Vp, it connects, closed switch, it connects through R1, R2 by C. This is V control. Okay. So, your Vp gets connected to this circuit and your control voltage will be will vary depending on your Vp, and it will vary based on your for only during the time the switch is closed. So, I am not solving this particular part, but I am just writing your V control whatever the previous value it had, because it has a capacitor, right. So, based on this particular capacitor, what you will see is that this voltage will increase, and just drawing it, do not go by this curve, I am just drawing it like this. Okay. This voltage, whatever voltage it has, it will be proportional to Vp for sure. I am not writing the exact equation, but this is how something it will look like. And then when both of them turns high, that time either you can say both of them turn high. So, this voltage will effectively be 0, right. So, whatever you are applying 0 to this resistor, right. So, your voltage may come down when both of them may come down something, and then it will remain. This is what will happen. Okay. Now, to implement this, so if you think about it, what we have done so far is this information is passed to the control voltage with this kind of voltage change, right. So, effectively I am not writing this delta V here in equation, this delta V is going to be proportional to the time delta t, the phase error which you have. Okay. So, this is like a voltage based implementation for the phase error to the control voltage. In contrast, you have a current based implementation where you again use two switches with two current sources like this. Okay. So, you have this switch controlled by up, this switch controlled by down, both the current sources are equal, okay, and this is getting connected to the loop filter. Why am I using this loop filter? We will see it later, but assume that this is the loop filter which we have right now. Earlier you can recall actually that we need an integrator. So, the capacitor is playing the part of an integrator. We need the proportional path. So, here resistor is playing the part of the proportional path. Okay. That is how we came up with like this simple loop filter. Now, we are interfacing our PFT with the loop filter in place of the previous one using voltage sources. Here we are using current sources. Okay. So, this is what we have. Now, in this case again you look at the same up and down pulses. So, if my up happens to be like this, okay, and down signal is like this, these are amplified up and down signals, this is actually my phase error or delta t error. So, what will happen here is when up signal is high, your switch is going to be closed from the top side, your V control voltage will actually increase. Okay, it will increase like this. When up and down signals both are high, right, the current from the top flows to the bottom, no current flows to the V control, right. If no current flows, the voltage should actually remain constant. Okay. So, previously ICP was flowing, but now ICP does not flow. So, you will retain the change in the voltage. Okay. So, this voltage variation which you have delta V control, this is also proportional to your delta T. Previously, I did not write for the exact expression or exact waveform here, because here you will see an exponential settling with respect to R1 and R2, whereas in this case there is no exponential settling, the current directly goes through the loop filter. So, if I want to write an exact equation, I can even write it V control of T is ICP goes through R. So, you are going to get a voltage here. So, that is ICP R plus you are integrating current, right. So, ICP times dt. So, this appears to be a very simple expression. You see ICP times R a jump here, and the continuous increase which you are seeing, right, that is this term. Okay. So, this particular implementation appears and happens both to be easier than the implementation which you just saw before using voltage sources, right. So, what we are going to do is we are going to use this particular implementation in our PLLs to convert the PFT output to control voltage. Now, for the same thing, we need to find from this PFT to the loop filter. So, let me first draw the block diagram how our connections will look like. So, I have current source, then I have another current source with a switch, and then it is like this. Okay, this is ICP, and this goes to a loop filter which is RNC1, which is controlling our VCO, and this is fed back. Do this. Okay, this is a reference signal, this is your output signal, this is V control, right. These are your up and down signals. So, here you have already seen the phase frequency detector. This block is called as charge pump. It pumps the charge in the loop filter. Okay. This block is our loop filter. Okay. And this particular phase lock loop is very standard and common, and it is called as charge pump based PLL. Okay. So, we have seen that how we used it here. Now, in order to analyze it, we need to know the gain of this charge pump. So, this is little tricky here, that if you look at PFT plus charge pump just here, let me remove these. So, these are up and down signals which are controlling the switches. So, this is up, this is down, you have ICP and so on. So, now you look at specifically, you focus on this part, right. If the previous instant happens to be one thing which you are seeing is PFT is detecting the phase error every reference clock period, right. It is not detecting in between the reference clock period, it happens only during the whenever you get the rising edge on reference. So, when you get rising edge on reference, you get rising edge on up and so on. So, I can write V control of n times T r as V control voltage of n minus 1 times T r, where T r is my reference period, right. This voltage, whatever the phase error you have, for that duration I am integrating the charge. Okay. This ICPR you are seeing ICPR during the transition, but at the end the voltage here, what you see at the end, this voltage change is only due to the capacitor. Okay. So, the change, this control voltage V control at NTR is V control n minus 1 TR plus ICP integrated for time delta t over capacitor C1. Okay. And this delta t which we are referring, this delta t is the phase error in the previous cycle, which I can write, this is for n minus previous cycle n minus 1 TR cycle. This can be written as V control of n minus 1 TR plus ICP by C1. I will multiply and divide by 2 pi. So, 2 pi delta t over the reference period times TR here, right. This is equal to V control of n minus 1 TR plus ICP by 2 pi TR by C1, okay, into phase error of 2 pi delta t. I can say this phase error at n minus 1 TR. I am writing this in a discrete form right now, because that is how things change here. I am looking with the average change in the control voltage change at every reference cycle. This I will convert it into Z domain, okay, because it is a discrete domain. So, V control of Z is equal to V control of Z into Z minus 1 plus ICP by 2 pi into TR by C1 Z inverse of phi error of C. Okay. Take the terms on one side, V control of Z as ICP by 2 pi TR by C1, right, into Z inverse divided by phi error of Z 1 minus Z inverse, okay, which is ICP by 2 pi TR by C1 1 by Z minus 1. Now, this is the transfer function from the phase error to the control voltage when you are assuming that the phase error information is actually getting converted to the voltage using the charge pump. And in this particular case, I have neglected one thing, that when I am writing this V control ICPT, I am only looking at this change from the previous value. So, what in two reference cycles, what was the value in the first previous reference cycle and what is the value in the current reference cycle. So, that change. This analysis is neglecting actually this part. If you take this into account, it becomes little cumbersome. So, I will just neglect that part right now. So, V control of Z by phi error of Z, right. Here Z is equal to e power s t r. Okay. Then for frequencies, for omega, frequencies omega TR much less than 1, right, I can e power STR is equal to 1 plus STR approximately under this approximation. So, I can convert this into S domain and write V control of S, this is Laplace domain by phi error of S as ICP by 2 pi TR by C1 into 1 plus STR minus 1, this goes off, right. So, this is equal to ICP by 2 pi, TR gets cancelled into 1 over SC1. Okay. All this math is to tell you that from phase error to the control voltage, if I assume that the role is played only by the capacitor, right, then what you are seeing is from phase error to control voltage, there is a gain of ICP by 2 pi. Okay. So, and that particular, so what are the units for this? You will see the units ICP by 2 pi as ampere per radian. Okay. So, this whole block, I will mention it again, this whole block PFT plus charge pump can be treated as a one single block with gain as ICP by 2 pi. So, I can model both our PFT plus charge pump. CP is normally used for charge pump, goes into the loop filter, controls the VCO and feeds back. Okay. The gain of PFT plus charge pump is ICP by 2 pi. Okay. That goes to loop filter and we can use Laplace domain to analyze this block now, okay, which we will see soon in the next session. Okay, so this is out, this is R. So, what did we do? We introduced how to convert the PFT output to the control voltage. We looked for two options. We found that the charge pump based option was appears to be much easier to implement. So, then we implemented charge pump using ideal switches and ideal current sources. Right now, we figured out the gain, combined gain of PFT plus charge pump, and then we derived the small signal model of a simple type 2, there is an integrator here, type 2 order 2 charge pump based PLL. Okay. Thank you.